In this video, we're going to look at the transformation effects of scale changes on equations and graphs. Although there is similarity between the graph translation theorem and the graph scale change theorem, there is a major difference between the transformations. Translations shift graphs. Scale changes stretches graphs. For instance, apply the scale change rule in which xy is mapped to ax by to the graph of the original relation. When you multiply x by a, it has the effect of stretching the graph horizontally, meaning if you were to grab the left and right sides of the graph, either you would stretch it inward or outward depending on the value of a. With y being multiplied by b, it has the impact of stretching it vertically. In order to come up with a new equation for the image, you will need to take the x's and replace them with x over a's and the y's with y over b's in the original pre-image sentence. There are various types of scale changes. A dilation is a transformation in which a figure grows larger, while a compression or contraction is a transformation in which a figure grows smaller. You can also have a reflection in which a transformation to a figure is the mirror image of itself. For this, and many of our upcoming examples, we will be using the quadratic parent function as our pre-image. Let's take a look at the impact of a horizontal scale change, and we'll begin by seeing its impact on 0, 0. Which really has no impact because the point will remain 0, 0. Why is that? Well, remember, 0 is going to be multiplied by a, 0 is going to be multiplied by b. 0 times anything is going to stay 0. What was once a valuable point when using translations is become very irrelevant because it does not move. So we're going to need to use other points. And the points I've chosen to look at are going to be 2, 4, which maps to 8, 4, and negative 1, 1, which maps to negative 4, 1. Now remember, this is a horizontal scale change, which means the graph is being pulled outward horizontally. Other points that would have been mapped would have included 1, 1 going to 4, 1, and negative 2, 4 going to negative 8, 4. Reviewing our various image points, we see that a horizontal scale change has no impact on a y-coordinate. It does, however, have an impact on the x-coordinates. In fact, in this case, our x-coordinates are multiplied by 4. We would then say that this graph has been horizontally stretched by a magnitude of 4. Another way of saying that is saying a horizontally stretched by a factor of 4. Now that we have our scale change mapping, we can say the value of a is equal to 4, and b will equal 1 because y's were not being affected. So when we apply the graph scale change theorem, y will be replaced with y over b, x will be replaced with x over a. And since x is squared, x over a quantity will be squared. I did not write y over 1 because that really has no impact. On the other hand, I did write x over 4 that needs to be squared. And when simplified, works out to be y equals 1/16 x squared, or x squared over 16. We move on to a vertical scale change. 0, 0 still does not change, it remains at 0, 0. But 2, 4 will now be mapped to 2, 8, as negative 1, 1 is mapped to negative 1, 2. In this case, the graphs have been stretched upward. Therefore, 1, 1 would have gone to 1, 2, negative 2, 4 would have gone to negative 2, 8, and this particular vertical scale change rules is where t of xy is mapped to x comma 2y, which affects the graph by vertically stretching it by a magnitude of 2. Since our y's are being multiplied by 2, b will be equal to 2. As x's remain the same, a will stay 1. So when we go y divided by b, we'll go y divided by 2. Since x is being divided by 1, we're not going to worry about that and we'll leave it alone. And when we multiply both sides by 2, we come up with y equals 2x squared. Before we continue on with scale changes applied to mathematics, let's take a look at scale changes applied to art, specifically clip art. For instance, this cartoon car, when a horizontal scale change could be applied, we can now make it into a limousine. Or we can compress it into a compact. Your choice. A vertical scale change can make the car very short, or it could make it very tall. But in all these cases, we've distorted the original graph. On the other hand, if we want to maintain the clip art's original proportions, otherwise known as its aspect ratio, we will need to apply a size change. That's where we take the clip art, grab it at its corner, and resize it that way. We might make the car very small, we can make it slightly large, or we can make it really, really large. But in all cases, the proportions are still the same. So returning back to mathematics, a size change means A equals B. Now 0, 0 still remains 0, 0. But in this case, 2, 4 is going to go to 8, 16, as negative 1, 1 is going to go to negative 4, 4. And if we take into account our other points, we realize that x and y are both being multiplied by 4. This graph is being horizontally and vertically stretched by a magnitude of 4. And when we apply that math to the original parent function, y will get divided by 4, x will get divided by 4. And since x was squared, x divided by 4 is squared, which then gives us y over 4 equals x squared over 16. But after multiplying both sides by 4, we can either rewrite it as y equals 1/4 x squared or x squared over 4. Having found the equation of my image, I'm now asking myself a new question. Was this size change the only way to get to y equals 1/4 x squared? And what I find out is, no, it is not. I could have done this solely using a horizontal scale change in which 2, 4 is mapped to 4, 4, negative 1, 1 is mapped to negative 2, 1, and where all the x coordinates are multiplied by 2, essentially stretching the graph horizontally by a magnitude of 2. So if my value of a is 2, and I go y divided by 1 equals x over 2, all quantities squared, I can recreate y equals 1/4 x squared. And once I realize I can use multiple scale change rules to recreate my image, I'm going to come up with alternate approaches. This time, we'll use just a vertical scale change. 2, 4 can be mapped to 2, 1, negative 1, 1 can be mapped to negative 1, 1/4, and we could continue this rule by multiplying all y's by 1/4, which would vertically stretch the graph by a magnitude of 1/4, or compress the heights by 1/4. Since b would equal 1/4, y divided by b means we'll go y divided by 1/4. But when you divide by a fraction, you would multiply by the denominator's reciprocal. So I could rewrite the left side as 4y equals x squared, and then when I divide both sides by 4, I come back to the image y equals 1/4 x squared. I also want to show you that it is possible to horizontally and vertically stretch this graph and not use a size change and still come up with the same y equals 1/4 x squared. If we were to take 2, 4 and map it to 1236, and negative 1, 1 and map it to negative 6, 9, our rule would be t of xy goes to 6x, 9y, which means the graph would be horizontally stretched by a magnitude of 6 and vertically stretched by a magnitude of 9. With a equaling 6 and b equaling 9, we apply the graph scale change theorem, where y gets replaced with y over b, or y over 9, and x gets replaced with x over a, and since x over a needs to be squared, that would be x over 6 quantity squared. We can square the quantity, coming up with x squared over 36, and then multiply both sides by 9, and 9x squared over 36 would reduce to y equals 1/4 x squared.